Pascal's law. A change in the pressure applied to a fluid is transmitted undiminished to every point of the fluid and to the walls of the container. So we can see an application here for the hydraulic press. So if you look at this system, it's basically designed to lift this car up. And we have on one side of the hydraulic lift a force F1 that is being applied with a perpendicular area A1. And this force causes a displacement of this piston by an amount delta x1. And on the other side, we have area A2, perpendicular area A2, and force F2, which causes a displacement delta x2, so the car is rising. So it's lifted up. Okay, now you can see that if this force per area here was greater than the force per area on this side, this would not be in equilibrium and the car would be lifted even more. So we must have the force per unit area on the two sides equal, and that's basically a result of Pascal's law. The pressure applied on one side is transmitted to any other side of the fluid and to the walls of the container undiminished. Now, the volume of the fluid that we displace here, delta x1 times A1, must also be equal to the extra volume we gain here, which is delta x2 times A2. So we have the volume of the fluid is conserved. A1 delta x1 is A2 delta x2. So that gives us A2 divided by A1 equals delta x1 divided by delta x2. On the other hand, Pascal's law tells us that this pressure that we apply here must be equal to the pressure that we see on this side, because this is transmitted undiminished to every point of the fluid. That is equal to F2 over A2. So F1 over A1 equals F2 over A2. So F2 over F1 would be equal to A2 over A1. But at the same time, A2 over A1 is delta x1 over delta x2. So you can see that F2 delta x2 equals F1 delta x1. Basically, this is the work done by this force F2, and this is the work done by this force F1. So we have energy input into the system, F1 delta x1, which is equal to the energy that we spend, F2 delta x2. So this is conservation of energy to lift this car up. Okay, so basically Pascal's law in this case gives us a statement of conservation of energy. Work done on the left side must be equal to the work done on the right side of the hydraulic press. Okay. Let's look at a few examples. In a car lift used in a service station, compressed air exerts a force on a small piston that has a circular cross-section of radius 5 centimeters. This pressure is transmitted by a liquid to a piston that has a radius of 15 centimeters. Part A, what force must the compressed air exert to lift a car weighing 13,300 newtons? Part B, what air pressure produces this force? Okay, so on the left side of the car lift, we have a radius R1 equals 5 centimeters. And on the right side, we have R2 equals 15 centimeters. And the weight that we are trying to lift is 13,300 newtons. We want to know the force we have to apply and the air pressure that will produce this force. So the area on the left side is equal to, because we have a circular cross-section here, circular cross-section, we must have area 1 equals pi r1 squared, which is pi 5 centimeters, 5 times 10 to minus 2 meters squared, this gives us roughly 7.85 times 10 to minus 3 meters square. And for the right hand side, we have a cross-sectional area pi r2 square, which is equal to pi 15 10 to minus 2 squared. So this gives us 70.69 times 10 to minus 3 meters squared. Now the pressure on the right side must be equal to the pressure on the left side. This is a Pascal's law because it's transmitted by the liquid undiminished. F1 over A1 must be equal to F2 over A2. So we see that the force F1, the force that the compressed air must exert, should be equal to A1 over A2 multiplied by F2. So if we plug in the numbers, we have an area A1 7.85 times 10 to minus 3 meters square, A2 70.69 times 10 to minus 3 meters square, and the F2 is basically the weight of the car, 1.33 times 10 to 4 newtons, and this gives us a force F1 of 1.48 times 10 to 3 newtons. Okay, so basically we note here that what we call F2 is W, weight of the car. Now what air pressure produces this force? The pressure is F1 divided by A1, so this will be equal to the force that we have calculated, 1.48 times 10 to 3 newtons divided by 7.85 times 10 to 3, 10 to minus 3 meters squared. So this gives us a pressure of 1.88 times 10 to 5 pascals. So the air pressure we need in order to achieve this is 1.88 10 to 5 pascals. Another example, estimate the force exerted on your eardrum due to the water when you're swimming at the bottom of a pool that is 5 meters deep. Density of water is given. So we have to estimate the surface area of the eardrum. So one can see that surface area of the eardrum, that is approximately 1 times 10 to minus 4 meters square or 1 centimeter square. So that's roughly the surface area. Now when we are at the bottom of this water, at the bottom of the swimming pool, we're going to see the atmospheric pressure plus the additional pressure due to the water, and we have seen that the pressure varies with depth, and it's P0 plus rho water GH in this case. So this is the pressure applied by the water. Okay, and inside the ear we have atmospheric pressure. So outside the ear we have the pressure applied by the water, and inside we have atmospheric pressure, so that we're going to see the difference in pressure on two sides of the eardrum is due to the water rho GH. which is equal to 1000 kilograms per meter cube times 9.8 meters per second squared times 5, which is 4.9 times 10 to 4 pascals. And the force that will be exerted on the eardrum will be due to this pressure difference multiplied by the area of the eardrum. So that will be 4.9 times 10 to 4 times 1 10 to minus 4 meters square, our estimated area. So we will see that the force will come out to be 5 newtons. Once again, this is an application of Pascal's law. The pressure that we see at the bottom of the swimming pool is basically the pressure that is applied to our ear as well. It's basically applied to the walls of the container undiminished. Another example, the force on a dam. Water is filled to a height capital H behind a dam of width W. So this is the width W of this dam. Height is capital H. Determine the resultant force exerted by the water on the dam. So you can see here we have atmospheric pressure applied from the surface of the water, atmospheric pressure applied from the other side of the wall, and we have the pressure inside basically varying with depth as we go down in the water. So we can calculate the pressure on the walls. It's going to be the pressure due to atmospheric pressure plus rho g h when we are at a distance h from the top of the water, and then we have atmospheric pressure on the other side, so this will be equal to rho gh. So remember that the pressure that we see here at this level, P0 plus rho gh, is also the pressure that is applied to the walls of the container due to Pascal's law. So the pressure varies as a function of distance from the bottom of the water. So it's going to be rho g h. Well, h is basically this capital H minus y, the distance to the bottom of the water. So we have capital H minus y. Capital H minus y is equal to h. And the force that we see for this infinitesimal area here, because this is the region where we have not an appreciable change in y, and therefore the force is approximately a constant. So dF is equal to pressure as a function of y times dA. So this will be equal to rho g capital H minus y, our pressure, times the area. Well, for the area, you can see here we have the width W multiplied by dy. So this is going to be W dy. And the force, the total force that we will see on the wall will be the integral P dA. So this will be integrated as y goes from 0 to capital H all the way from the bottom to the top of the water. This will be rho g capital H minus y W dy. So the force will become rho g W hy minus y squared over 2 when we integrate it, and this will be evaluated between 0 and capital H, and that will give us a force of 1 over 2 rho g omega capital H squared. So this will be the total force that we will see appearing on the wall of the dam. that's exerted by the water. Okay, and finally, how do we measure pressure? One method is the Mercury Barometer. So you have this tube filled with mercury and the top is basically empty, it's vacuum, so the pressure there is zero. The pressure at point A must be equal to the pressure at point B. This is due to Pascal's law. And what is the pressure at point A? It is the density of mercury times gravitational acceleration g times h. It will be the pressure here plus rho gh, but the pressure here is zero. So it is just rho gh. But the pressure at point B is equal to the atmospheric pressure. It's due to the air outside. So this is basically used to measure atmospheric pressure, which has a value of 1 atmosphere, 1.013 10 to 5 pascals. So we can calculate h, the height of this mercury column, as P0 divided by rho g. So, and we can see that this density of the mercury is 13.6 10 to 3 kilograms per meter cube. When we substitute the numbers here, the corresponding column height is 760 millimeter mercury. So atmospheric pressure, 1 atmosphere, corresponds to 760 millimeter mercury. Another setup used to measure the pressure of a gas contained in a vessel. You can see here this vessel contains a gas that has pressure P. And the other side is basically open to air and filled with some fluid, for example mercury. Now the pressure at point A must be equal to the pressure at point B. If it was not, if it was more, then this would be rising, right? So the equilibrium, the strict equilibrium requirement. And what is the pressure at point A? The pressure of the gas. What is the pressure at point B? Atmospheric pressure P0 plus rho gh. So we see that P0 plus rho gh is equal to the pressure of the gas P. So P is our absolute pressure of the gas, and P minus P0 is called gauge pressure. So it's the pressure measured relative to atmospheric pressure. So we can basically calculate the gauge pressure of this gas, or measure the gauge pressure of this gas using this setup from a measurement of the height of this column. Okay, so in summary, we talked about Pascal's law, which states that the pressure applied to a fluid is transmitted undiminished to every point of the fluid and to the walls of the container. The hydraulic press application shows us that if we use conservation of the volume of this fluid, the volume displaced must be equal to the volume that is added on top on the right hand side. And Pascal's law, the pressures on two sides must be equal. We see that this basically states that the work done by the force F1 must be equal to the work done by force F2 when we move the car up. We talked about a numerical example for a car lift where we had A1 and A2 given, so we can just calculate the force that we need given that we know the weight of the car that we want to lift. So this is basically our F1, and the pressure that we have to apply is F1 over A1. We basically estimated the surface area of the eardrum to be 1 centimeter square, and we calculated the force that the eardrum would feel at the bottom of a pool that is 5 meters deep. Basically, we used the fact that the pressure varies with depth. So P0 plus rho gh is the pressure at the bottom of the swimming pool, but on the other side of the eardrum, we have atmospheric pressure. So the gauge pressure here is rho gh, and that basically gives us the force as delta P times the area of the eardrum, surface area. As an application of a pressure that varies with depth here, we calculated the force using dF equals PdA for a pressure that varies with location. And when we are at a distance h from the surface of this water surface, we are also at a difference capital distance y from the bottom of the pool. We see that h plus y is equal to capital H, or h is equal to capital H minus y. So the pressure on the walls should be equal to the pressure due to this water minus the pressure due to the outside air. So it's P minus P0. So the pressure difference, so we see P0 plus rho g h minus y appearing on the left side, P0 appearing on the right side. So the net pressure is rho g h minus y multiplied by the area W times dy gives us the incremental force that we see on this side of the wall. And by integrating this force PdA for y varying between 0 and capital H, we calculate the total force F, 1/2 rho GW H squared. And finally, we talked about how to measure pressure. Mercury barometer is used to measure the atmospheric pressure, where the height of the column tells us what the atmospheric pressure should be, because we have equal pressures at points A and B. The pressure on one side is rho gh, on the other side is atmospheric pressure, and we've seen that 1 atmosphere corresponds to 760 millimeter mercury. Open tube manometer is another setup used to measure the pressure of a gas, and basically if this is an open ending on one side, this pressure will be measured with respect to the atmospheric pressure. P minus P0 is equal to gauge pressure, where this pressure differential will be given by the pressure due to this fluid here, which can be mercury, for instance. So it would be equal to rho gh.